Hey everyone, how goes it? Welcome back to Computer Science 311. Today we're going to talk about synchronization examples. In a previous lecture, we presented the critical section problem and focused on how race conditions can occur when multiple concurrent processes share data. We went on to examine several tools that address the critical section problem by preventing these race conditions from ever occurring. These tools range from low-level hardware solutions to increasingly high-level tools. We also discussed various challenges in designing applications that are free from race conditions, including liveness hazards such as deadlocks. Now, we are going to apply these tools presented in the previous lecture to several classic synchronization problems. The bounded buffer problem, which was previously introduced, is commonly used to illustrate the power of synchronization primitives. Here we present a general structure of the scheme without committing ourselves to any particular implementation. In our problem, the producer and consumer processes share the following data structures: an int n, which corresponds to the number of buffers each item can hold, a semaphore mutex that's assigned the value of 1, a semaphore full that's assigned the value of 0, and a semaphore empty that's initialized to the value of n. We assume that the pool consists of n buffers, each capable of holding one item. The mutex, or binary semaphore, provides mutual exclusion for access to the buffer pool and is initialized to the value of 1. The empty and full semaphores count the number of empty and full buffers. The semaphore empty is initialized to the value of n. The semaphore full is initialized to the value of 0. The code for the producer process is shown here. The code for the consumer process is now shown here. We can interpret this code as the producer producing full buffers for the consumer, or conversely, as the consumer producing empty buffers for the producer. Now that we understand the bounded buffer problem, let's take a look at a different kind of problem. This one is called the readers-writers problem. Let's suppose that there exists a database that is to be shared among several concurrent processes. Some of these processes may want to read the database, whereas others may want to update the database. We distinguish between these two types of processes by referring to the former as readers and the latter as writers. Obviously, if two readers access the shared data simultaneously, no adverse effects will result. However, if a writer in some other process, either a reader or a writer, tries to access the database simultaneously, chaos may ensue. To ensure these difficulties do not arise, we require that the writers have exclusive access to the shared database while writing to the database. This synchronization problem is referred to as the reader-writers problem. The reader-writer problem has several variations, all involving priorities. The simplest one is referred to as the first readers-writers problem, and it requires that no reader be kept waiting unless a writer has already obtained permission to use the shared object. In other words, no reader should wait for other readers to finish simply because a writer is waiting. The second readers and writers problems require that once a writer is ready, that writer performs its write as soon as possible. In other words, if a writer is waiting to access the object, no new readers may start reading. A solution to either problem may result in starvation. In the first case, writers may starve. In the second case, the readers may starve. For this reason, other variations of the problem have been proposed. Now we present some solution to the first readers and writers problem. In the solution to the first readers-writers problem, the reader process shared the following information data structures. The binary semaphores mutex and RW mutex are both initialized to 1. Read count is a counting semaphore initialized to 0. The semaphore RW mutex is common to both reader and writer processes. The mutex semaphore is used to ensure mutual exclusion when the variable read count is updated. The read count variable keeps track of how many processes are currently reading the object. The semaphore RW mutex functions as a mutual exclusion semaphore for the writers. It is also used by the first or last reader that enters or exits the critical section. It is not used by readers that enter or exit while other readers are in the critical section. The code that we see here is the code for the writer process. Now the code that we see here is for the reader process. Note that if the writer is in the critical section and N readers are waiting, then one reader is queued on the RW mutex and N-1 readers are queued on the mutex. Also observe that when the writer executes signal RW mutex, we may resume the execution of either the waiting reader or a single waiting writer. The reader-writer problem and its solution have been generalized to provide a reader-writer lock on some systems. Acquiring a reader-writer lock requires specifying the mode of the lock, either a read or write access. When a process wishes only to read shared data, it requests a reader-writer lock in the read mode. A process wishing to modify the shared data must request the lock in write mode. Multiple processes are permitted to concurrently acquire a reader-writer lock in read mode, but only one process may acquire the lock for writing, as exclusive access is required for the writers. Reader-writer locks are most useful in the following situations. In applications where it is easy to identify which processes only read shared data and which processes only write shared data. Alternatively, in applications that have more readers than writers. This is because read-writer locks generally require more overhead to establish than semaphores or mutual exclusion locks. The increased concurrency of allowing multiple readers compensates for the overhead involved in setting up the read-writer lock. Now let's consider another classic problem, the dining philosopher's problem. Consider, in this case, 5 philosophers who spend their lives thinking and eating. The philosophers share a circular table surrounded by 5 chairs, each belonging to one philosopher. In the center of the table is a bowl of rice, and the table is laid out with 5 single chopsticks, as we can see here. Now, when a philosopher thinks, they do not interact with their colleagues. From time to time, a philosopher gets hungry and tries to pick up 2 chopsticks that are closest to them. A philosopher may pick up only 1 chopstick at a time. Obviously, they cannot pick up a chopstick that is already in the hand of their neighbor. When a hungry philosopher has both of their chopsticks at the same time, they eat without releasing the chopsticks. When they are finished eating, they put down both chopsticks and start thinking once again. The dining philosopher's problem is considered a classic synchronization problem not because of its practical importance, but because it is an example of a larger class of concurrency control problems. It is a simple representation of the need to allocate several resources among several processes in a deadlock-free and starvation-free manner. One simple solution is to represent each chopstick with a semaphore. A philosopher tries to grab a chopstick by executing a wait operation on that semaphore. They release their chopstick by executing the signal operation on the appropriate semaphore. Therefore, you can think of the shared data as being an array of semaphores called chopsticks, which in this case are of size 5. Now for this data structure that represents the chopsticks, all of the elements are initialized to 1. Now we can see here, this is the structure of the philosopher. Although this solution guarantees that no 2 neighbors are eating simultaneously, it nevertheless must be rejected because it could create a deadlock. Suppose that all 5 philosophers become hungry all at the same time, and each one grabs their left chopstick. All elements of chopsticks will now be equal to 0. When each philosopher tries to grab the right chopstick, they will be delayed forever. Several possible remedies to the deadlock problem are as follows. Allow at most 4 philosophers to be sitting simultaneously at the table. Allow a philosopher to pick up their chopstick only if both chopsticks are available. Now, to do this, they must pick them up in a critical section. Or use an asymmetric solution. That is, an odd number of philosophers picks up their first chopstick and then their right chopstick, whereas an even number philosopher picks up their right chopstick and then their left chopstick. Now, while these solutions may prevent a deadlock, it doesn't eliminate the possibility of starvation. So now we're going to illustrate this monitor concept by presenting a deadlock-free solution to the dining philosopher's problem. This solution imposes the restriction that a philosopher may pick up their chopstick only if both of them are available. To code this solution, we need to distinguish among 3 states in which we may find a philosopher. For this purpose, we introduce the following data structure. An enum where the properties are thinking, hungry, and eating. A philosopher at an index I can set the variable at state I by setting it equal to eating only if their 2 neighbors are not eating. We also need to declare another data structure called self. Now this allows the philosopher I to delay themselves when they are hungry but are unable to obtain the chopsticks they need. The distribution of the chopsticks is controlled by a monitor that in this case is called dining philosophers. Each philosopher before starting to eat must invoke the operation pickup. This act may result in the suspension of the philosopher process. After the successful completion of the operation, the philosopher may eat. Following this, the philosopher invokes the method putdown. Thus, philosopher I must invoke the operations pick up and put down in the following sequence. Now, it is easy to show that the solution ensures that no 2 neighbors are eating simultaneously and no deadlocks will occur. In this chapter, we have brought up classic synchronization problems and how we can utilize the synchronization tools like mutexes and semaphores in order to solve them. With all that being said, I'll see you next time.